All right, so welcome tonight to our chat on algorithms and specifically sorting algorithms in Ruby. So we're going to look at a few tonight and see where we go. I can tell you up front that I am not a person with a computer science degree, so these things are not innately pounded into my mind at a very low level. So I kind of learned them along the way as you guys are going to. So some of the questions I might not be able to answer, but please feel free to shout out any questions you have at all, and we'll dive into them, even if we just Google them together and figure it out. So sometimes I wonder about what Ruby's actually doing. Like the fact that we can do something like let's say 1.18.4.72 and call sort on it, and it comes back to us. Let's just open IRB here. There. Do something like 1.18.4.72. That sort. It comes back 1.4.18.72. So easy for us. It's what's actually going on here, because we know that the word sort isn't the logic. We know that Ruby has logic built into these methods that are supplied for us, these native methods. So, and honestly, the understanding sorting algorithms has very little to do with the actual act of sorting. It's really that the different algorithms are great examples of various techniques that can be applied to a large set of problems. So we're going to look at a couple different things and their implementations in Ruby. So to have kind of a base, we're going to assume that we're going to write methods that will use algorithms that will take an array of integers that's arbitrary length, negative or positive or anything in between, but integers, and then sort them in ascending order. And then if we wanted them descending, we could just call reverse. We don't really need to worry about that. Or we could, edit the algorithm relatively simply. So we're going to go through some things and walk through them and let me know if they're making sense to you. So the first thing that we're going to look at is the bubble sort. And I think I actually have a graphic that I can show for this. Yeah. I get this. Into a window over here. Sweet. This is kind of a visual of what bubble sort does. If you're really interested in diving deeper into these topics, you can look up, it's called 4 semesters of CS in 6 hours. It's actually also, you can find it, but there's also a video series on Lynda where Brian Holt talks about it. You can typically get a Lynda subscription for free through your local library. with your local library card. I have one. I didn't even have to go to the library. I signed up for it online and got access to everything on Lynda. It's pretty cool. Check it out. Lots of top level coding courses and lectures are on there. So yeah, there's a resource that is probably going to take a lot of your time. So don't dive too deep into it. But if you're really interested in this type of stuff, I found this to be very helpful. It's all in JavaScript though, so know that. But there's kind of a visual of what mobile sort is going to do for us. Getting back to our code. The idea is pretty simple. So we're going to walk through the list and put two adjacent elements in their descending order. And then the thing is, we have to go through the list over and over and over again until we don't make any more swaps. So the idea of, we have a 2, then we have a 0, and then we have a 5, and then we have 7, and we have 4. We go through the list and we look at two elements. We say, okay, there's a 2 and a 0. Those aren't in order. So we want to swap them. Okay, now they're swapped. And then we walk through the next. Say 2 and a 5. Okay, those are fine. 5 and a 7. Oh. Here's a 5 and a 7. Those are fine. Here's a 7 and a 4. Okay, we need to swap those. We go to the list and we change it. Now we have 4 and 7. And then we repeat that over and over and over again until we get our sorted list. Not the quickest, however, it is very straightforward. So we wanted to do this in Ruby. I think I'm just gonna bang away at this and then we'll walk through and talk about it. Bang away at typing it out. An array. We need to know how long it is. Always put my ends, so I don't forget. And we're going to go through this in just a second, step by step. Array I, array, wait, array I, right, there we go, plus 1 equals, array I, that one, and break. It'll be so awesome. Break is not swapped. Like, you're never going to find that code. That's code. And it makes complete logical sense. Break if not swapped. Okay. So what's going on here? Kind of showed you the example of, what we're trying to do. We're trying to compare two values, swap them if they're out of order, and continue through and keep on doing that over and over and over again until they're all in the proper spot. So we maintain a variable called swap. So this is true if any swaps were made in the past through the array. So we're going to go through the whole array. We have the length of the array is n, so n minus 1 dot times. So we're going to say, if it would be 4 here. So 4 minus 1 is 3 dot times do. And at the end of that walkthrough, swapped is false. meaning there have been no swaps performed, we stop, we return the array. So essentially, swapped equals true is how we end this loop that's going to go on forever figuring out our sort. So bubble sort, because it's slow, is bad at scaling. Pretty much because of how it's doing this. If, let's say, there was an input of an array that was in descending order, so opposite of what we wanted to do, this means that we would have to perform the maximum number of iterations to get to the end. So assuming that every swap is running at a consistent amount of time, the time that it takes increases, I think, to a factor of 4, if my understanding of this topic. It's quadratically, which I believe is a factor of 4. I know quad is 4. So it's not good at scaling. It's not very efficient, but it is very, very kind of simple to look at. This does, however, is a method that will sort what's called in place. So we don't have to use any other memory outside of the memory that the array is taking up initially to sort, because we're just moving the values around. We're swapping them in place. So memory-wise, it's relatively efficient. It's going to use only as much memory as what the data that we give it. However, as far as things go, it doesn't scale well. So, we're saying in here, if the element that we're on is greater than the element after it, then we're swapping them in their place. We're setting swap to true. And that's bubble sort. Is that making sense in the grand scheme of things? Okay, I see silence. I'm going to keep. Okay, but the break if not swap does. So the only time we're going to get, so what our loop is doing is we have this loop, and this loop is going to run until we hit a break. Now, we're not going to get that. So if not swapped, means swapped is going to equal false. Every time we go through this iterator, we're going to set it equal to true. So the loop is going to start. We're going to set this variable swap to false. We're going to iterate through the entire array of values that we passed in. If we swap any of them, which is this part right here, if a value, if we just think visually, on the left is greater than the value on the right in our array, so let's say 18 and 4, we're comparing those two right here, then we're going to swap them. When we swap them, we're going to change that swap value to true. Then we're going to get here, and we're going to say, if not swapped. So right now, this is true. because we said it on line 12. We're going to say if not swapped. So swapped is true, so it's not swapped. It is swapped, sorry. It's not swapped. It's just a little, I can see, kind of we're checking to see if this is false, pretty much. The verbiage does make it a little more complicated. And we're saying we're only going to break if swapped is false. But it's not false. So that means our loop continues on.
Is that another way to say break if swap does not equal true? The not swap part?
Not swapped. Yes. Because we're going to evaluate swapped, what it's equal to. So this could be an integer, it could be a variable. We're going to say swapped. We're going to get to the Boolean of that. So if swapped equals false, then we want to know what is swapped. It comes back false. So we know not swapped is true. We're saying if, we know if is going to evaluate truthy or falsy, and then we say not swapped. So the opposite of swapped. So if it's still false, that's going to tell if true. And if it's true, which it would be if there was a swap made, and not swapped, it's going to be false. That's going to say, okay, we're not breaking this time. You can use the word not instead of equals false. I wouldn't want to say that exactly. Not is, we could do that if that's a little clearer. Not is equivalent to just saying, you know, the opposite of in the Boolean sense. Let's go back and look at different sort. If I can find the visual. Merge. This is what we'll look at next. It's just personal preference, using not versus the bang symbol. That's all there is to it. Because if I were to speak this code to you, I would say break if not swapped. That's how I would verbally say that. So it's just one of those things. Ruby is very flexible in how you can do what you want to do. Some people prefer the verbiage that Ruby allows because they really like it, and you know, it allows you to almost feel sometimes like you're writing pseudocode, but you're actually writing code. And then other people just, you know, think about things a little bit differently. Like I'd probably write it with the bang character and not the word not, just because that's what I'm more familiar with. But yeah, it's just one of those things that Ruby allows. To each their own. Let's look at merge sort. So oh, in 5 in IRB. I was like, no, I was just trying to illustrate what not swapped is equal to. So if swapped, when swapped is true, not swapped is false. I guess. Yeah, here's not swapped, same thing. I forget that not is just Ruby, so we can run it in IRB, same way. So what merge sort does, as we can kind of see in visual, is it takes a more divide and conquer technique. So I think you can kind of see how it's, doing sections at a time and kind of then connecting them together, merging them together, as opposed to our bubble, which is working through the entire thing at the same time. Slowly but surely pulling it all together versus merge, which is, we can see multiple sections getting sorted a little bit and then being pulled together, eventually looking almost like 2 lines getting merged to 1. That's good. Oh. So basically what merge sort is going to do is sort, the first way we did the array, but now we're going to do the left half of that array and the right half of that array and then combine them. So we're going to break that up into smaller sections so that, we're just a little bit more efficient with it. And the way that we do this is we're going to break up each of the halves even further into halves. So we have, we have 8, let's say we have 8 elements, and we break that into the left side of 4 and the right side of 4. Then we break those in half, and then we have the left side of 2 and the right side of 2, the left side of 2 and the right side of 2. And eventually, we're going to reach an array of size 1, which we know technically automatically sorted. And then we're going to take all of those pieces together, combine them, and eventually are equivalent to our sort method. However, this does get a little bit involved when we're combining them all. So let's say we have 2 sorted arrays. Let's look at 1, 3, 5, and 2, 4, 7. And we want to combine them into one sorted array. So in this case, we're going to take a look at the first elements of both arrays and put the smaller one into our final array. So after one run, we'll have this. Now, we're going to repeat this process, except we're going to move along in the array, making the next element the first element. So in this case, we're not going to get rid of it, but let's act like it's not there anymore. So it's like, now we're looking at, I don't know how, looking at something more like this, as far as what our sort is doing in merge sort, in the idea. So we're looking at our 3 and comparing it to our 2. So we keep doing this until we've run out of elements from one of our lists. So we have our 2 lists, and we're sorting them, our arrays that we've broken up. So we'll end up something that looks like this. 1, 2, 3, 4, 5. And we know we pretty much eliminated all of those now. And we know that we have 2 sorted arrays. So the rest we just push on in order. 6 and 7. Just add 6 and 7 to the end. So we use the procedure in this example as our merge or combine or what have you. So looking at this, here's kind of our pseudocode. We have our array. So a couple things we have to take into consideration. We're going to return A if n, which is our array length, goes out to 1. Because if it has 1 element, it's sorted. That's just how it is. Our second thing that we have to handle is we're going to have left, which is going to be our left half, A, and right, which is our right half of A. And then we're going to need to sort those. So we're going to have a sorted left and sorted right. Let's say merge sort left. Merge sort right. And return our merge. Have a sorted left, a sorted right. So that is our outline, our pseudocode of what we need to do to make merge and how merge sort works. It splits it up and sorts it using merge sort, then it combines it back together, doing what we outlined, comparing the first element of each. So we see how this can use a little bit more memory. It's not being sorted in place. We're making copies, we're doing different things. This one is definitely more involved, code-wise. So I'm actually going not type this one out. We can still look through it. So we see 30 lines of code here. There are some breaks in here, though. Let's clear this. So you can see better. Probably don't need this right now. There we go. You can see all the code. And let's see. Yeah, there we go. That's probably better to see. So this is how merge sort would be written. There, perfect. So we have to do our list. So we define our merge function inside of our merge sort function. And merge is probably the more interesting part of this. Because jumping down the arrays a bunch of times is, I think, relatively straightforward. So we're going to look at, return array spliced, if array spliced dot length less than or equal to 1, and then we're going to iterate through our array. So we set a midpoint of our array, set to this array slice that we're passing in. Which we're passing in from here. So we're setting up two kind of helper methods pretty much. We have this method and this method inside of this merge sort method. So we have merge sort iterator. We call the iterator and we pass in our original array. We return that if less than or equal to 1. So that's our first step. Return a n equals 1. Then we get a midpoint by getting the length divided by 2 minus 1. We then slice to that point on the left and the right, and we return to our merge function with our left and our right. So here, we have our function, which is res, standing for result. So we set up as an empty array, and we have our left and our right representing our two halves. So we know what where we're at in each side of the array as we're iterating through it. So if our R is greater than the length of our right sorted array, and our L is greater than our left sorted array length, then we're going to break because we know we've gone through them. So else, or if we're not breaking, then we're looking at, excuse me, we're comparing our right and left sides. We're shoveling into our result. So R being our right side, iterator, greater than or equal to our right side array's length, or L is less than or equal to the left sorted side array's length, and the left sorted current value is less than right sorted value, current value. Then we're going to push our left array's current value into the result and increment. If that's not true, we do it with the right side. Eventually we get a result and return that. So I think when you dive into it and really look at it, it's not as difficult to parse. It is more intricate for sure, but I think it's a lot of small pieces that are put together to do something much larger. So like this merge sort iterator, nothing too complex is happening. Finding the midpoint, we're creating two arrays from that midpoint, we're returning it. As long as it's greater than or equal to 1, the length of the array. We're throwing that in here. We're defining what happens when we get to the end of one of the sides. And then we're doing some comparison to see if the value that we're currently looking at on the left is greater than or equal to the value that we're currently or greater than or less than the value that we're looking at on the right side. If not, we're doing the opposite. So you're probably wondering, what's the benefit of like, this is way more complicated than what we just looked at, right here. No, this is definitely more complicated than just calling dot sort, which is just fine and works fine and well as well. But This is much more efficient. And we could say if the array, say, had a million values, bubble sort would be 17,000 times worse than merge sort in performance. That's why there is a point to doing something a little bit more complex, because it is more efficient. If you get really interested in these, array slice. That is the array slice argument at the bottom method really array to be sliced? Yes, this is the original array. So we call merge sort iterator with array, and that array is referencing the original array that's passed in to the method. So yeah, I guess original array is probably more accurate. Don't want to use the same word array only because it would get confused, and it would be using this one. But yeah, I think original array might be a better word here, or a better argument name. So merge sort shows us a nice strategy, this divide and conquer method. And it turns out that there's a bunch of problems which are solved by breaking them into smaller problems and combining the result with smaller results. And it really takes time and skill and practice to know when a specific sort might work better than another one, where, you know, the divide and conquer idea is the best way to go. And the base idea is if you have a very simple base case, so in merge sort, a list of length 1, for example, or we're able to somehow break our problem down to this case and have some kind of idea to combine solutions, divide and conquer might be the best avenue to explore. So there's another way that we can do things. This is following the same kind of idea of merge sort, something that's a little bit better though. We'll call it mark sort. And here we're going to take our array again. We're going to look at a max. And min. And say marking 0 and array next minus array min plus 1 each 2 so x marking x array min. Okay. Almost done. There's our result. An iterator. That thing. That times up. That's not a dot. 2. There we go. So and then let's see. That's so we have an array called markings here. And that is representing the number of times a number occurs in our array. And each index of markings is going to correspond to a number in the range array max, array min inclusively. So we initialize our markings array with zeros. So we're saying to set up an array of zeros, and we're going to multiply it out. That many zeros are going in there. And then we walk through the array and increment a number when we see it occur in the array. And that's what we did. And then finally, we print out the numbers. We print out the numbers, seeing the right number of times. So we're making a few passes on our array to get to this. However, we're not making a nested loop with this. So we're still more performant. So this is actually really fast when it comes into the world of speed. However, we could potentially use a giant piece of memory to do this. So we have our trade-offs here. For example, if we looked at an array that was 1 and 1 million, 2-element array, the amount of memory that we would allocate with this mark sort is a 1 million element array. However, if we know our element range is going to be low or small, or we just know that we have a ton of memory, this is a very useful algorithm. So, looking back some, as we're coming up on the last 10 minutes, we looked at bubble sort, looked at merge sort, and we looked at mark sort some, not as in-depth. And we see that there's so many different ways to accomplish the same end goal. And there's different reasons to use each one. That's +1. So if we look at here, if we want to fill it with enough, let's see. All right. Let's say array equals 1 and 1 million. Excuse me. So we have array.min 1, array.max is 1 million. So array.max minus array.min is going to be 999,999. So if we want to get all the values inclusively, we're going to have to add 1 to that. Because right now, if we counted starting at 1, the beginning of this array, we would end up at 999,999, and we want to get to 1 million. So we take that, and we add 1 to it, and we get that inclusivity. Because we're not just counting the in-between, but the elements at each end as well. So we have to add to it by 1. Good question. Asking why, I guess I should say that out loud. Why on line 68, we have that +1 there for markings. Yes, and we've seen that, different array or different algorithms for different things can be useful. And knowing our use cases, if we ever choose to implement our own type of algorithms for things. And they're not just sorting. Sorting is the most common thing, I think, that is dealt with. But there are other things that are done with algorithms. So really just knowing your use case and what, if you're really looking at implementing algorithm level things, knowing your hardware, knowing what you need to optimize for. Like we were saying, if we know that our numbers are always going to be a small range, then something like this could work really well, because we're not going to worry about memory. Or if we know that we just have memory everywhere to spare, then maybe it's worth it. Or if we know that, we're not going to have really large things, then we might do something like bubble sort, where we know it's very memory conscious. So it's being sorted in place. Or maybe we need something in the middle a little bit, merge sort. It's really about knowing our use cases when it comes to implementing algorithms and differing algorithms that achieve the same thing. Ultimately, I think the people who write development languages like Ruby or any other language that you might write code in is going to have an implementation of sort that works really well for most cases. I honestly don't know. See if we can find out. Ruby sort method. What's the algorithm behind the Ruby sort method? Which algorithm does Ruby sort method use? It does natively use quicksort, so it's using quicksort, which is another way to sort. There's lots of sorting algorithms out there. There aren't other built-in methods, so this is from 2009. I don't think that would have changed. So if you wanted to use a different type of sort, you have to write your own, or find one. So doing something like this. And depending on your use case, you could actually write a sort method that would replace the built-in Ruby sort method. It's not advised to ever replace any of that. It would be much better to do something like, a bubble sort that when you're using a different method, especially when you're working with other people who are assuming that, it's the default method. But yeah, if you wanted to use a different type of sort, you would have to write it yourself or find it out there. There is this thing called Big O. I'm just going to tell you the complexity and the efficiency of algorithms. It has a whole bunch of them listed. These are data structure operations and array sorting algorithms. Time complexity, space complexity, Big O notation. It's been explained to me once, but I still can't grasp it. So I'm not the correct person to ask about this. But I do know these are all different sorting methods. And it shows their complexity level. And green is better, red is worse. But yeah. These are all different ones, I think. Yeah, it goes to Wikipedia. So this Big O cheat sheet, it's pretty cool. They have a poster, which I guess if you ever need to know that type of stuff, you can get it. But I know people who know this type of stuff and understand this, and it's cool. But also something that I don't think I'll be attacking anytime soon. Like I said towards the beginning of the lecture, I talked to people who've been doing development for years, 15 plus years, and they explicitly told me, if you're doing web development, while it's cool to know these things, you don't need to know them. You won't get into a place where you're dealing with problems physically that are such low level that you need to understand these types of computer science level things until you get to a much higher level. So the person I'm specifically thinking of right now is doing a master's in computer science because he's finally reached a point where he's like, I should probably know this stuff because the types of problems that I'm being tasked with solving and tasking others to solve deals with this type of stuff. But it's still kind of cool to know that it's out there and you could possibly have questions like this asked by an interviewer, depending on their background or the types of applicants that they typically get. Ultimately, I know people have computer science degrees doing web development. They say it doesn't help them at all, typically, from their first-person experience. So they don't believe that understanding things like Big O and such are beneficial to the average, to the working web developer, because at this point in time, hardware has caught up. Moore's law, the things that we're doing online are just not, the processors are able to handle it to an extent that they weren't in the past when we really had to worry about, okay, I need to pick the right sort because I have 1 gig of RAM on most computers type of thing. Oh, keep getting emails. Sorry about that. I had to turn that little thing off. But yeah, that's what I got tonight. And I hope you enjoyed. Before you go, I do have one more thing. Let me stop this recording of this lecture.